Okay, in today's lecture we're going to cover the section 1.7 material on linear independence. So let's start by defining what linear independence is. So let's suppose that we have a set of vectors v1, v2 up through vp in Rn, so these are n-dimensional vectors. This set of vectors is said to be linearly independent if the following vector equation, x1 times v1 plus x2 times v2, and so on, up through xp times vp, is equal to the zero vector, has only the trivial solution, where all of these weights, x1, x2, up through xp, are zero. So linear independence means that the only way that we can take a linear combination of this set of vectors, or of these vectors, and arrive at the zero vector is by taking all of the weights, x1, x2, up through xp, as zero. Now, on the other hand, we would say that this set of vectors, v1, v2, up through vp, is linearly dependent if there exist weights c1, c2, up through cp, which are not all zero, such that the linear combination c1 times v1 plus c2 times v2 up through cp times vp is equal to the zero vector. So if it's possible to find a linear combination of the vectors where the weights are not all zero, such that we can get the zero vector as our linear combination of these vectors, they're said to be linearly dependent. And in the case of linear dependence, so in this case, the relation between these vectors is what is called a linear dependence relation among the vectors v1, v2, up through vp. So specifically, a linear dependence relation among the vectors would be the linear combination of these vectors, which gives us the zero vector without having all of our weights c1, c2, up through cp equal to zero. All right. So let's consider an example for determining whether a given set of vectors is linearly independent or dependent. And throughout this section, we'll look at some different results, which will allow us to determine pretty quickly in some cases whether a set of vectors is linearly independent or dependent. So in this first example, we have the set of vectors v1, v2, and v3, and we are asked to determine whether these are linearly independent. And if they happen to be linearly dependent, we want the linear dependence relation among these. So let's think about what we're asking. To determine whether a set of vectors is linearly independent, we want to know whether the linear combination x1 times v1 plus x2 times v2 plus x3 times v3 can be made equal to the zero vector. And we want to know whether this equation has only the trivial solution, where x1, x2, and x3 all have to be zero, or whether there are non-zero values for these weights, which would give us the zero vector. So to answer that question, we can think about this vector equation as a matrix equation. So let's consider the corresponding augmented matrix. So the augmented matrix for this vector equation would be the matrix whose columns are these vectors, v1, v2, and v3. So our first column would be 1, 2, 3. Our second column is 4, 5, 6. and our third column is 2, 1, 0, and we're setting this equal to the 0 vector. So on the right-hand side of our augmented matrix, we have the 0 vector, 0, 0, 0. So what we're really considering here is a homogeneous linear system of equations, and we want to know whether we have only the trivial solution or whether we have a non-trivial or non-zero solution. And we saw in our section 1.5 work that the only way a non-trivial solution exists is if we have a free variable. So to determine whether or not we have a free variable, we need to row reduce this matrix. So let's start by simplifying here. So in our first row, we have a lead coefficient of 1. So I'm going to use that pivot to eliminate the 2 and 3 in my second and third rows. So my first operation, I'm going to take row 2 minus twice row 1. So my first row will remain as 1, 4, 2, 0. My second row, we get negative 2 plus 2 is 0. Negative 8 plus 5 is negative 3. Negative 4 plus 1 would be negative 3, and 0 plus 0 is 0. And in this same operation, I'm going to simplify in my third row by taking row 3 and subtracting 3 times row 1. So we have a negative 3 plus 3 is 0. Minus 12 plus 6 is negative 6. Minus 6 plus 0 is negative 6, and 0 plus 0 is 0. So at this stage, we can see pretty quickly that our second and third rows are identical, or scalar multiples of one another. So it looks like we will have a free variable here. But to simplify a bit further, our augmented matrix, well, in my first column, or first row, I have a lead coefficient of 1 with zeros above and below it in that first column. In my second row, I have a lead coefficient of negative 3, and I want it to be a positive 1. Now we notice that everything in our second row is divisible by 3, so an easy way to get a 1 there would be to take negative 1/3 of the second row. So our first row I'm going to leave alone as 1, 4, 2, 0. Dividing the second row by negative 3, we have 0, 1, 1, 0. And in this same step, I know that the negative 6 that appears below that pivot in the second row, I want to have as a 0. So an easy way to get a 0 there would be to take that negative 3 as the lead coefficient in my second row, multiply by negative 2, and add it to the third row. So that is take row 3 minus 2 times row 2, which would give me 0. 6 minus 6 is 0. Again, 6 minus 6 is 0. And 0 minus 0 is 0. So at this stage, I see that I have a row of all zeros. And if I want to simplify this a bit further, well, here we have a 1 in the lead position of our first row, zeros above and below it. A 1 in the second row with a 0 below it, but I need to eliminate the 4 that appears above that pivot of 1 in the first row. So to do that, in my last step here, I could take row 1 minus 4 times row 2, which makes my first row 1. Negative 4 plus 4 is 0. Negative 4 plus 2 would be negative 2 and 0. My second row remains 0, 1, 1, 0, and then we had our row of zeros. So this matrix is now in reduced row echelon form, and we see that we only have pivot positions or pivot columns in the first two columns. We do not have a pivot in that third column, which means that x3, or our third variable, is a free variable here. So x3 is a free variable. And we find from our first two equations, well, our first equation tells us that 1x1 is equal to 2 times x3. And our second row in this matrix, or our second equation, says that 1x2 is equal to negative 1x3. Since there is a free variable for this system, that means that there is a non-trivial solution of this homogeneous linear system. So if there is a non-trivial solution, that means that these vectors are linearly dependent. So let's start by saying, hence, these vectors, v1, v2, and v3, are linearly dependent, which was the first part of our question, determine whether they are linearly independent. So here we've shown that they are, in fact, dependent. And then the second part of the question said, well, if they are linearly dependent, find a linear dependence relation among them. So I need to determine non-zero weights such that the linear combination of these vectors would be equal to the zero vector. So here I just need to find a choice of x1, x2, and x3. Now, since x3 is a free variable, I can choose x3 to be anything I want. So maybe an easy choice we could take if x3 was equal to 1, then we have x1 would be equal to 2, and x2 is the negative of x3, which would be negative 1. So for our linear dependence relation among these three vectors, we would take x1, which was 2, times v1, plus x2, which was negative 1, so plus a negative 1 or minus 1 times v2, plus x3, which was 1 times v3, and that is equal to the zero vector. So this linear combination of my three vectors, which is equal to the zero vector, is the linear dependence relation that I'm interested in. Now, of course, we see that there's more than one valid choice here. If we chose x3 to be 2, then x1 would be 4, x2 would be negative 2. So there's, in fact, infinitely many ways to write a linear dependence relation among these, depending on what value we choose for our free variable. Okay. So what we've just considered is expressing this linear combination of our vectors in terms of an augmented matrix. So let's consider the following sort of problem. Let's suppose that we begin, instead of with a set of vectors, with a matrix A whose columns are a given set of vectors, A1, A2, up through AN. So here, the matrix capital A is the matrix whose columns are A1 up through AN. And we can write a linear combination of these vectors A1 through AN instead of a vector equation as a matrix equation. AX is equal to the zero vector, which is equivalent to the vector equation by taking the linear combination of A1 through AN and setting it equal to 0. So every linear dependence relation that we would have among the columns of A corresponds to some non-trivial solution of AX is equal to 0. So recall, if we have a non-trivial solution, that means there's a free variable. So there's infinitely many choices of that free variable, and we just saw in the previous example that every choice of our free variable would lead to a different linear dependence relation among these columns of A. So another way that we could say this is that the columns of a matrix A are linearly independent if and only if the matrix equation AX is equal to 0 has only the trivial solution x equals 0. So let's look at another example where we're working with a matrix that has a given set of column vectors and determine whether they are linearly independent. So here we have a matrix A, which is a 4 by 3 matrix, and the columns of this matrix will denote as A1, A2, and A3. And we want to know whether these form a linearly independent set. So we want to consider whether the matrix equation AX equals to 0 has a non-trivial solution. Or equivalently, does our augmented matrix A have, or does that system have a free variable? So let's consider the augmented matrix for this system. So here our first column is -4, 0, 1, 5. Our second column is -3, -1, 0, 4. Third column is 0, 4, 3, 6. And we're looking at a homogeneous linear system. So we're augmenting that coefficient matrix A with the 0 vector. So let's perform row reduction on this matrix in order to get our matrix into row echelon or reduced row echelon form. So here, I know that in this first row, I would like my lead coefficient to be a +1. So there's several ways that I could go about getting a +1 there. One way would be to maybe add row 4 to row 1. Equivalently, or an alternative way I could do this, I see that I have a 1 as the lead coefficient in the third row, so I could just interchange row 1 and row 3. So I'm going to go with that approach. Let me, in my first step, switch row 1 with row 3. So that would make my first row 1, 0, 3, 0. My second row is 0, -1, 4, 0. My third row is now -4, -3, 0, 0. And my last row is 5, 4, 6, 0. All right. So now, in my first row, I have that leading coefficient of 1 that I want. I'm going to use that to eliminate the -4 and +5 in the third and fourth rows. So in my next step, I'm going to take row 3 and add 4 times row 1. So my first row will remain as 1, 0, 3, 0. My second row, I'm going to leave alone for right now. I have 0, -1, 4, 0. And when I perform this operation on my third row, I get 4 minus 4 is 0. 0 minus 3 is -3. 12 plus 0 is 12. And 0 plus 0 is 0. And in the same step, I'm going to take row 4 and subtract 5 times row 1, which makes my fourth row -5 plus 5 is 0. 0 plus 4 is 4. -15 plus 6 is -9. And 0. So now, I have for my first row that leading coefficient of 1 with zeros above and below it. In the second row, this leading coefficient is -1. I want it to be a positive 1. So in my next step, I might start by taking the negative of row 2. So my first row is 1, 0, 3, 0. And when I take the negative of row 2, I'm going to have 0, positive 1, negative 4, 0. And then in this same step, well, for that one leading coefficient, or the -1 leading coefficient in the second row, I want to eliminate the -3 and positive 4 that appear below it. So to get rid of the -3, well, I could take row 3 and subtract from it 3 times row 2. So I would have a 0, positive 3 minus 3 is 0, minus 12 plus 12 is 0, and 0 plus 0 would be 0. And in the same step, to eliminate the leading 4 in my fourth row, I could take row 4 and add to it 4 times row 2. So I would have 0, negative 4 plus 4 is 0, and then 16 minus 9 would be 7, and 0 plus 0 is 0. So now, in my third row, I have a row of all zeros, and in the row following that, I have 0, 0, 7, 0. So I know I want any non-zero row to appear above a row of all zeros. So in my next step, I'm going to interchange the third and fourth rows. So changing row 3 and row 4. And maybe, let's see, before I do this, let me simplify another way to save myself a little bit of work. So in that last row, I have 0, 0, 7, and I know I want the leading coefficient to be a 1. So an easy way to get that there would be to divide that fourth row through by 7. So taking 1/7 of row 4, I have 1, 0, 3, 0, 0, 1, negative 4, 0. My row of all zeros, and then 0, 0, 1, 0. So now, in this last step, I'm going to go ahead and interchange those third and fourth rows. So that is switch row 3 and row 4. And in this same step, to get this in reduced row echelon form, I know I need to eliminate the positive 3 and negative 4 that appear above that leading 1 in that fourth row. So to get rid of the positive 3 in the first row, I could take row 1 minus 3 times row 4, which would give me 1, 0, 0, 0. To get rid of the negative 4 in my second row, I could take row 2 plus 4 times row 4. So I have 0, 1, 0, 0. And then interchanging the third and fourth rows, I now have 0, 0, 1, 0, and a row of all zeros. So finally, this matrix is in reduced row echelon form. And we can see that we have a pivot in each column. Therefore, the only solution of this homogeneous linear system is the trivial solution, since we don't have a free variable. Equivalently here, we can see our first, second, and third rows of this matrix tell us that x1, x2, and x3 all have to equal 0. So x1, x2, and x3 are 0, which means the columns of this matrix A are linearly independent. Recall we had linear independence provided that we only had the trivial solution of our system, which is what we're seeing here. Okay. So in this next part of the section, we'll consider a special case of linear independence or dependence in the case that we're working with a set of only a single vector or two vectors. So the easiest set that we could be considering would be a set of only one vector. So let's say that we have a set with the only vector being some vector v. Then this set, which consists of the single vector v, is linearly independent if and only if the vector v is not equal to the zero vector. And the reasoning for that is if we only have a single vector, well, taking a linear combination of that single vector would be an equation of the form x1 times v1. So if we're setting that equal to the zero vector, then the only way that we have the trivial solution is, or only the trivial solution, is if the vector v is something other than the zero vector. Now, if the single vector in our set is the zero vector itself, that set is considered to be linearly dependent because any scalar multiple or linear combination of the zero vector is equal to zero, even if we choose non-trivial solutions or non-zero values for x1. So when we're considering a single vector, as long as we have something other than the zero vector, that single vector is considered to be linearly independent. And if we have the zero vector, it is considered to be linearly dependent. Now let's suppose that we have a set of two vectors, the next easiest case. So a set of two vectors, v1 and v2, is considered to be linearly dependent if and only if one of these vectors is a scalar multiple of the other. So let's suppose, or let's see why that's true. So let's suppose that these are linearly dependent. So that means that there exist non-zero weights C1 and C2 such that the linear combination of V1 and V2 is equal to the zero vector. So I could solve this equation for V1 by taking V1 is equal to, I've got a typo here, negative C2 over C1 times V2, or equivalently, if I solve this equation for V2, I would have V2 is equal to negative C1 over C2 times V2, V1. I'm sorry about these typos here. So if we have a linearly dependent set of two vectors, that means that we have some non-trivial solution of the following vector equation. And if I solve for one of those vectors, I see that my vector v1 is either some scalar multiple of v2, or v2 is a scalar multiple of v1. So the only way that a set of two vectors can be linearly dependent is if one is a scalar multiple of the other. So using that information, let's consider the following example where we're given a set of two vectors and we're asked to determine whether they are linearly independent. So here we have v1 and v2. So let's see if they are scalar multiples of one another. So by comparing their first components, 2 and negative 6, well, to get negative 6 from 2, we would multiply by the scalar negative 3. Now let's see if that would hold for the second components as well. Here our second components are -1 and +3. So we see, indeed, if we were to multiply -1 by -3, we would get that +3. So in this example, here we find that V2 is equal to -3 times V1. So they are scalar multiples of each other. Or another way that we could write this would be as 3 times V1 plus 1 times V2 is equal to the 0 vector. So we found a linear combination of these vectors V1 and V2 with weights 3 and 1, which is equal to the 0 vector. So since we were able to find non-zero weights such that the linear combination is the 0 vector, that means that these vectors are linearly dependent. All right. Let's consider part B. We have the vectors V1 and V2. And we want to know whether these are linearly independent or dependent, so we can see whether or not they are scalar multiples. So comparing the first components, well, we have 2 and 4. So the first component of V2 is twice the first component of V1. So let's see if that holds for the second component. So here the second component of each vector is 5. So if we were to multiply the first vector by 2, we would have 4, 10, not 4, 5. So these are not scalar multiples of each other. So here we might say something like clearly V1 and V2 are not scalar multiples of each other. So these are linearly independent vectors. If they were linearly dependent, one would be a scalar multiple of the other. So here we have a simple way for sets that consist of either 1 or 2 vectors to determine whether these sets are linearly independent. Now let's think quickly about what the geometric meaning of this condition for linear independence means for 2 vectors. So if we have 2 vectors, they are linearly independent as long as they do not lie on the same line. So vectors are linearly dependent if one is a scalar multiple of the other, but let's think about what that means geometrically. So in our first example, part A, let's think about the representations of these vectors in the plane. So say this is in the x1, x2, or xy plane. Our first vector, v1, was the vector 2, -1. So if we draw its representation, its position vector representation, we would have the vector whose initial point is the origin, and our terminal point would be 2, 1. This is our vector v1. Now, the vector v2 is -6, 3. So its position vector would be the vector whose initial point is at the origin, and the terminal point would be this point 6, 3. So if we draw its representation, v2, we see that v1 and v2 lie on the same line, since they're scalar multiples. To get v2, we just took -3 times v1, so we're reversing the direction of v1 and multiplying it by a factor of 3, so tripling its length. We can see that from our diagram here. So if our vectors lie on the same line through the origin, or same line in general, then they are linearly dependent. Whereas in our second example, part B, we had linearly independent vectors, and these would not be scalar multiples of one another, therefore they would not lie on the same line. Okay. Now, in the last part of our section, we'll consider more complicated cases if we're working with sets of two or more vectors. How can we determine linear dependence or independence? Based off what we saw in the case of a set of two vectors, we arrive at the following theorem. This is theorem number 7 from your textbook. So in this section, I'm going to number my theorems because we'll reference some of these in some later examples. And this theorem gives a characterization of linearly dependent sets of vectors. So let's suppose that we have an index set of vectors, we'll call it S, containing vectors v1 up through vp. So this set contains two or more vectors, let's say. So P is at least 2. Then this set would be linearly dependent if and only if at least one of the vectors in our set can be written as a linear combination of the other vectors. So let's think about why that might be true here. In the case of two vectors, we saw that one would be a scalar multiple of the other vector. So what if we have more than just 2? So these vectors are linearly dependent if there exist non-zero weights, or weights which are not all 0, such that the linear combination C1 V1 plus C2 V2 up through CP VP is equal to the 0 vector. So as long as not all of these weights are 0, then I can solve for one of my vectors, at least one of my vectors, in terms of the others. So let's say, for instance, that C1 is non-zero. We know that at least one of these weights is non-zero. So for instance, if the first weight was non-zero, then I could solve for V1 in terms of the other vectors by first subtracting all of the other terms to our right-hand side. So I would have negative C2 V2 minus C3 V3 up through CP VP. And then if C1 is non-zero, I could divide both sides through by that constant C1, and I now have found V1 as a linear combination of the other vectors V2, V3 up through VP. So this theorem says, well, if we have a linearly dependent set of vectors, at least one of those vectors is a linear combination of all the others. Now, a word of warning about this theorem. One thing that this theorem does not say is that every vector in a linearly dependent set is a linear combination of the preceding vectors. So it just means that at least one of my vectors is a linear combination of the others. It doesn't mean that any one vector in that set would be a linear combination of the others. Given that information, let's look at the following example. Here we are asked to determine all of the values of H for which this set of vectors, here we have 3 vectors, are linearly dependent. So we know that these are linearly dependent if there is a linear combination of these equal to the 0 vector. So let's maybe name these vectors. Let's call these V1, V2, and V3. And we want to take a linear combination of these vectors, x1, V1, plus x2, V2, plus x3, V3, and set it equal to the 0 vector. Now, the augmented matrix for that linear system would be the matrix whose columns are these vectors, 1, -1, 3, -5, 7, 8, and 1, 1H, and we're augmenting that with the 0 vector, since this is a homogeneous system. Now we want to know what are the values of H that make these linearly dependent, so we need to have a non-zero solution of this system, which means that we need a free variable. So let's row reduce this matrix and find conditions on that constant H such that we would have a free variable. So here in our first row, we have a leading coefficient of 1, and I need to eliminate the -1 and +3 that appear below it. So starting with the -1 in my second row, I could simply take row 2 and add row 1 to it. So I have 1, -5, 1, 0. When I add the first row to the second, I get 0, 2, 2, 0. And in my third row, I'm going to take row 3 and subtract 3 times row 1. So that gives me -3 plus 3 is 0. 15 plus 8 would be 23. And then in the third row, let's see, we have a -3 plus H, or H minus 3, and 0 plus 0 is 0. So let's see if we could simplify a bit further here. So now in our leading, or in our second row, we have a leading position, our leading entry of 2. I want to have a +1 there. So we see everything in our second row is divisible by 2. So if I divide my second row by 2, I can get a leading 1. So this becomes 1, -5, 1, 0. My second row becomes 0, 1, 1, 0. And for right now, I'm going to leave my third row as 0, 23, H minus 3, 0. So now I have the leading 1s in my first and second row. I have 0s everywhere below the 1 in the first column. And in order to put this in row echelon form, I need to eliminate the 23 that appears below the 1 in that second row. So to do that, I can take row 2 minus 23 times, or excuse me, row 3 minus 23 times row 2. So my first row will stay as 1, -5, 1, 0. Running out of space here. Or let me maybe not squish this in here. So let me use the line below that. Keep this a little neater. So let's say we rewrite it down here. I'm going to take row 3 minus 23 row 2. So my first row is 1, -5, 1, 0. 0, 1, 1, 0 for the second row. And then performing this operation, I have 0, minus 23 plus 23 is 0. Then minus 23 plus H minus 3 gives me H minus 26, and 0 minus 0 is 0. So the matrix is now in row echelon form. And in order to have a free variable, well, I can't have a pivot in every column. Or equivalently, I can think about, well, I need a row of all zeros as this last row. So here we have a free variable. if and only if the value of h minus 26 is equal to 0, or equivalently if h is equal to 26. And if we have a free variable for a homogeneous linear system, that means that we have a non-trivial solution, and these vectors would be linearly dependent. So the value of h that I need here is 26 in order for these vectors to be linearly dependent. All right. Now, in the last part of this section, we'll consider a couple of theorems for which linear dependence of a set of vectors is immediate. So for the first of these theorems, Theorem 8, if a set contains more vectors than there are entries in each vector, then that set of vectors is linearly dependent. So what we mean by that is any set of vectors, v1 up through vp, that is a set of p vectors, which are vectors in Rn, or vectors within entries, this set will be linearly dependent if p is greater than n, if the number of vectors is greater than the number of entries in those vectors. Now the justification or proof of this is pretty straightforward. We can go through it here. So let's consider the matrix A, which has these vectors as its columns. So that is columns v1, v2, up through vp. Now each of those vectors is a vector in Rn. So this matrix A is an n by p matrix. So we have n rows, because these are vectors in Rn, in p columns, since we have p vectors and each one is a column. So if p is greater than n, then there are more variables or more columns than equations or rows. So if we're thinking about this as representing an coefficient matrix for a homogeneous linear system, we have more variables than equations. So that means there is at least one free variable. And if there is a free variable, that means that a non-trivial solution to the homogeneous linear system exists. So this system has a non-trivial solution, which means that the columns of A are linearly dependent. So for any set of vectors, if we have more vectors than the dimension, or than entries within each vector, automatically that set is linearly dependent. Now a similar, or well, another theorem that gives linear dependence immediately is the following, Theorem 9. So if we have a set of vectors v1 up through vp, which are vectors in Rn, and that set contains the 0 vector, that is the vector of all zeros, then that set must be linearly dependent. So that is any set which contains the 0 vector is linearly dependent. So let's think about why that's true. If we have the following set of vectors and it has the 0 vector in there, then by rearranging the order of these vectors, we may assume that the first vector, let's call it v1, is the 0 vector. If the first one was non-zero, let's say it was like v3 was the zero vector, well, I could just list v3 as the first vector and then have v1 as the 0 vector. That is the first in my index set. So I can rearrange them to put the 0 vector as the first one in our set. And then if I look at the linear combination of these vectors by taking 1 v1 plus 0 v2, 0 v3 up through 0 times vp, well, that would give me the 0 vector, because I'm taking 1 times the 0 vector, which is 0, and then zeros for every other weight of all the other vectors. So that leaves me with the 0 vector. But I've now found a linear combination of these vectors where at least one of my weights, namely this first weight, was non-zero. So I'm finding a non-trivial linear combination of these vectors that gives me the 0 vector. So the set of vectors S is linearly dependent. All right. So these two theorems give immediate ways to determine whether a set of vectors is linearly dependent. So in this next example, we are asked to determine just by inspection, so just by looking at these sets of vectors, whether the set of vectors is linearly independent or dependent, and justify each of our answers. So in part A of this example, we have 2 vectors in R3, or in space. Now remember, anytime that we're working with just 2 vectors, they are linearly dependent if one is a scalar multiple of the other, and they are linearly independent if they are not scalar multiples. So let's think about whether these 2 vectors are scalar multiples of one another. So looking at their first components, 4 and 6, well, to get 6 from 4, we would have to multiply by 3 halves, or 1.5. So let's see if that holds for the other components. If we take -2 and we multiply by 3 halves, we would indeed get -3. And if we take 6 and multiply by 3 halves, we would have 9. So in this example, if we give these vectors names, let's say v1 and v2, we could say that our second vector, v2, is equal to 3 halves of v1. So these are v1 and v2 are linearly dependent. So here, linearly dependent since they're scalar multiples of one another. Or equivalently from this relationship that we found, another way we could have justified this, this means that 2 times v2 is equal to 3 times v1. So 3v1 minus 2v2 is equal to the 0 vector. So we've got a linear combination of v1 and v2 with non-zero weights that's equal to the 0 vector, which is the definition of linear dependence. So let's look at our next one. In part B, we have the vectors v1, v2, v3, and v4. These are 4 vectors in space. So here we have a set of 4 vectors, but there's only 3 entries in each vector. So in the case that we have more vectors than entries in each vector, that theorem number 8 guaranteed that these were linearly dependent. So for our justification, we could say here we have 4 vectors in R3. That is more vectors than entries in each vector. So by theorem 8, the set of vectors is linearly dependent, or these vectors are linearly dependent. So here again we have dependence. And in part C we have the vectors v1, v2, and v3. So 3 vectors in R3. But we see that our second vector here, v2, is the 0 vector. And by theorem 9, any set of vectors which contains the 0 vector must be linearly dependent. So here, v2 is equal to the 0 vector. So by theorem 9, this set of vectors, or these vectors, are linearly dependent. All right. Now in our last example, let's consider the following. So we can use linear dependence or independence of vectors to come up with solution sets or solutions of homogeneous linear systems. So here, let's suppose that we have the matrix A, which is this 3 by 3 matrix. And if we're a little bit clever, we can observe that the first column of this matrix, 4, negative 7, 9, plus 2 times the second column, 1, 5, negative 3, is equal to the third column. So we are asked then to determine a non-trivial solution of A times X is equal to the 0 vector. So to work through this, let's give these columns of A names. Let's call these vectors, or columns, the vectors A1, A2, and A3. And from what we're told in the problem, the first column, which is A1, plus twice or 2 times the second column, A2, is equal to the third column, A3. So if we were to move everything to one side of our equation, we have 1A1 plus 2A2 minus 1 times A3 is equal to the 0 vector. So these columns are linearly dependent. We found a non-trivial or non-zero weights for these vectors such that a linear combination is equal to the 0 vector. So how can we use this to find a non-trivial solution of A times X is equal to 0? Well, let's consider that matrix equation. A times X equals to 0 is equivalent to the vector equation x1 times the first column of A, A1, plus x2 times A2, plus x3 times A3 is equal to the 0 vector. So to get our solution for the vector x, we need x1, x2, and x3 such that this linear combination of the column vectors is equal to 0. But using our earlier work, we immediately see what those weights are. here x1 is equal to 1, x2 is equal to 2, and x3 is equal to -1. So writing those weights as a vector, or that solution as a vector, we find that the solution, or one solution here, would be 1, 2, -1 for x1, x2, and x3. Now, of course, note that we could take our equation that we had in this line and multiply it by any non-zero scalar to get another non-trivial solution. So if I were to multiply this equation through by, say, -2, I would have -2a1 minus 4a2 plus 2a3 is equal to 0. So another non-trivial solution of that system would be -2, -4, +2. Or equivalently, any non-zero scalar multiple of this vector x would be a non-trivial solution. So in this section, we've introduced the idea of linear dependence or independence of a set of vectors, and looked at some conditions for when a given set would be linearly independent versus